what can you guys tell me that you remember from yesterday? Where might we have local extrema? Say that again, Ethan. Critical points, right? So the critical points are the points where we might have local extrema. And those are really the only places where we have to check for local extrema. If it's not a critical point, it cannot be a local extreme unless it's an endpoint. So if we're looking at a function on an interval, then the endpoints of a closed interval could also be local extrema or global extrema. So what we're going to do in each of these examples is we're going to locate the critical points first. And then once we've found the critical points, we're going to determine if those critical points are extrema or not. We could do any one of these by graphing them and looking at the picture, in addition to doing the calculus on it, finding the derivative and finding critical points. We'll do them all analytically first, and then we'll look at how we can use a graph to kind of help us out. This is a familiar function. This is a function that we know what it looks like. So once we do the calculus, we should be able to answer the question whether it's a minimum or a maximum fairly easily. But we'll talk about how we can use calculus to do that also. So to find critical points, what are we going to do first? Take the derivative, yeah, differentiate. So we're going to say f prime of x is equal to 2x. All right, so once we've found the derivative then, what do we do to find the critical points? We're going to set that equal to 0. So we're going to take this derivative and set it equal to 0. And so what do we get for x? X equals 0. So this is, and we want to be clear about what we're doing here. So in some way, say that this is your critical point. So we have a critical point at x equals 0 because that's where the derivative equals 0. A lot of times on the AP test, if you're asked to find a minimum or a maximum, you will get a point for finding critical points. So if you set the derivative equal to 0, that's saying that you're finding critical points, and you'll get a point for that on a free response question. So just this step right here, the 2x equals 0, is usually worth something. So be sure that you're showing that you're setting the derivative equal to 0. All right. Now, once we have the critical points, this is the only place when x equals 0 that could be a minimum or a maximum. So I want somebody to tell me whether it's a minimum or maximum and justify it. From what we know about this function right now, we know the function x squared looks something like this. So when x equals 0 right here, that's going to have to be a minimum because we know what the function looks like. You guys agree with that? Yes?
I was going to say if you took numbers bigger than it, it'd be bigger. If you took numbers smaller than it, it'd still be bigger. So.
Okay, good. So another way to do it, let's say we don't know what the function looks like. What we could do, one way we could do it, as Tilly suggested, is plug in some points around it. So let's say I don't know what the function looks like. We could, say, use a chart and say we want to know what f of x is around that point. So maybe we plug in a number just a little bit bigger than 0 and a little bit less than 0. So, I'm sorry, I should have put that in there. So when we put 0 in for x, we know this is going to be our critical point. So when we put 0 in for x, what are we going to get for f of x? 0. Let's say we put in a number a little bit bigger than x, say 0.1. What do we get for f of x? 0.01. And if we put in a number a little bit less than x, a little bit to the left, negative 0.1, what do we get? 0.01 again, right? So we can see here that the values to the left and to the right are going to be bigger than 0. Okay, now I like this. This works in simple cases, but what if there's a number closer to 0 than 0.1 that has a negative value? Now, we know what this function looks like. We know that it doesn't look like that. But let me just show you on a graph what I mean here. Let's say that we graph this. We have our point at 0, 0. We just got a point at 0.1, negative point, I'm sorry, 0.1, 0.01 there, and negative 0.1, 0.01 there. So we have points to the left and to the right that are a little bit bigger. What says that the function couldn't look like this? Oops.
X squared.
Okay, we know the x squared function doesn't look like that, but let's say we don't know what it looks like.
The exponent?
No? I'll tell you in this example, there are a few things that tell us that. For one thing, if it were to look like that, what would we have had here and here also? We would have had critical points there also, right? So we know because there weren't any other critical points that couldn't have happened. But the short answer is we would have to do a lot more work to figure that out. So we're going to, and like I said, I kind of like this way of doing it. I like the way of checking points around it. But there's actually an easier way. And it's a calculus way. So let's look at not the function itself, but the derivative around 0. So when x equals 0, sorry, let me change this again. So when x equals 0, what's the derivative? 0, right? You guys agree with that? What about to the left of 0? So over here, what's the derivative going to be if x is negative? So I'm just going to put any negative number in. It's going to be, the derivative is going to be, now we're looking at the derivative here. The derivative is going to be negative, right? Do you guys agree with that? What if we're looking at a positive x value? What's the derivative going to be? Positive. Okay, so tell me what this means. If the derivative is negative to the left of 0, what does that mean? The slope of a tangent line is going to be negative, right? So we know that the function to the left is going to be decreasing. Decreasing is going to be the word that we use for that. So we know the function is decreasing to the left of 0, and we know that since the derivative is positive to the right, it's going to be increasing. You guys have heard the terms increasing and decreasing before, right? That was on the first test that we took. So you were supposed to be able to identify that. So we know it's decreasing to the left and increasing to the right. So what does that mean at 0? It has to be it has to be. So the question is it a minimum or a maximum? It has to be a minimum, right? All right, so this is, and I'll show you a better way to organize this later. This is not the way I would have done it. But the idea here is if we look at the derivative to the left and to the right of that critical point, we can see if it's increasing or decreasing to the left and to the right, and then use that to determine if it's a minimum or a maximum, or possibly neither. All right, so we have a critical point at 0. We should go ahead and finish this and answer the question. So when x equals 0, we're going to get a minimum. So we're going to have and all we're worried about is local here. In addition to this being a local minimum, it's also a global minimum, but that's not important here. We have a local minimum at 0, 0. Okay, so we get this point from our critical point. We get this value by plugging our critical point back into the function. Cool? It's easy enough, right? This one doesn't look quite as easy. So we want to find all local extrema on this polynomial here. What's the first thing we're going to do? Take the derivative. All right, so the first thing when we want to find extrema is take the derivative. So we get 6x squared minus 6x minus 12. Now what? Okay, we'll set that equal to 0. So we have 6x squared minus 6x minus 12 equals 0. Any ideas how to solve that? Yeah, factor it. I would factor out that 6 first. So we have x squared minus x minus 2. And then that makes factoring a lot easier here. What do we get? x minus 2x plus 1. I'm just writing down what I'm here. Do you guys agree with that? What I'm hearing? Okay, so when are we going to get critical points?
When x equals 2 and x equals -1.
Okay, I agree with that. Now, we could use what we know about this polynomial, about, in this case, a cubic function, to determine whether or not those are maximums, minimums, or neither. But let's go ahead and use what we know about calculus to do that. So we've got our critical points. We know the critical points are going to be when x equals 2 and x equals -1. So what we want to do here now is we want to organize what we know into a chart. And we're going to look at the derivative here. So the derivative of the function between at these points here, we know the derivative here and here is going to be 0. So what we want to know is what's it going to look like between them, on the intervals to the left of -1, between -1 and 2, and to the right of 2. So what is the derivative going to be? If we plugged in, say, -100, really any number to the left of -1, what are we going to get in the derivative here? We could plug it in here, we could plug it in here, we could plug it in here. I like this one the best. If we plug in -100, we get a negative here, we get a negative here. Negative times negative is positive. So the derivative is going to be positive on that interval. From -1 to 2, I like when 0 is in an interval because 0 is really easy to use. So let's put in 0. If we put in 0 here, we get -2. Here we get +1, so we have a negative times a positive. It's going to be negative. So the derivative is negative on that interval. You guys following what I'm doing here? And then to the right of 2, plug in 100. Doesn't really matter. Anything bigger than 2, we get a positive times a positive, which is positive. All right, so on this interval, what do we know about the function? Since the derivative is positive, we know the function is increasing. Since the derivative is negative on this interval, we know the function is decreasing. Since the derivative is positive, we know here that the function is increasing. So anywhere we get a switch from increasing to decreasing, we're going to have a what? We're going to have an extremum. In this case, what'd you say? If it switches from increasing to decreasing, it's going to be a local maximum at, what's the point going to be? -1. Anybody figure out the y value yet? Oh boy, I'm hearing a lot of different answers. Alright, so at -1, 12. We're going to have a local maximum. Alright, then at this other critical point, the function switches from decreasing to increasing. So we're going to have a local minimum. That's going to be at the point 2, comma. I'm hearing mostly -15s. If anybody disagrees, shout it out, please. It's not too bad, is it? In the past, if I asked you to find local extrema here, it's something that you would have been able to do, but you would have had to use what? Your calculator. You guys all know how to do this on your calculator, right? Use your calculator to find a minimum and maximum. Now we can do it without. Pretty cool, huh? What are we going to do first? Find the derivative. So the derivative of e to the x squared is e to the x squared, and then times what?
2x.
Hope you didn't do that on the test, Cole. Okay. And then what? I mean, we could simplify that if we needed to, but we don't really need to, because what we need to do now is set the derivative equal to 0. So we'll say e to the x times 2x equals 0. And since we have two factors here, to figure out when this is equal to 0, we can set e to the x squared. Sorry, I forgot the squared there. We can set e to the x squared equal to 0, and we can set 2x equal to 0. Okay, so we need to figure out when each one of those is equal to 0. When is e to the x squared going to equal 0? Never. So we don't get any critical points out of this part of it, out of this factor. When is 2x equal to 0?
0.
At 0. So we get a critical point at x equals 0. Alright? We good so far? So we've found our critical point. Now we need to figure out if that critical point is a minimum, a maximum, or neither. It's possible that it won't be any kind of extrema. So what are we going to do to check that? Okay, we'll do the chart. We'll do the first derivative test. So we're going to look at the regions to the left of 0 and to the right of 0 on the derivative. How do I know, and I probably should ask this on the last problem, how do I know that within this interval here it's always going to be positive or always going to be negative, and it's never going to change? Anybody know how I know that? Or could it change?
You'd have another critical point.
I would have another critical point, exactly. So the derivative here is a continuous function. So a continuous function can't go from positive to negative without crossing through 0. And so if the derivative were to equal 0 somewhere, then we would end up with another critical point in there. So I know that between the critical points and on the ends, on the outsides of the critical points, the derivative is always going to be positive or always going to be negative. It's not going to change signs. The only places that the derivative can change signs is at the critical points. Okay, either where the derivative crosses through 0 or where the derivative is undefined. We haven't run into that yet, but it's possible that we'll get a derivative that's undefined, and that's another critical point. So to the left of 0, is the derivative going to be positive or negative? If we put in a negative number here, e to any power is going to be positive. So 2 times the negative whatever is going to be negative. How about to the right of 0? Positive. So thinking about what's happening with the function here, when the derivative is negative, that means the function itself is decreasing. Yes? And when the derivative is positive, the function itself is increasing. And so at this critical point, when x equals 0, the function changes from decreasing to increasing, which means that at that point we have a local minimum. And we put 0 in here. What is e to the 0?
1.
That would be e to the 1. Okay? We having fun yet? A little bit? Alright, cool. Same thing. We want to find any local extrema. What we're going to do first, take the derivative. So f prime of r is going to be quotient rule, low d high times 1, okay, minus high d low over, okay, and that is squared. All right. Now what? Okay. We want to set that equal to 0. That's going to be a lot easier if we simplify it, right? So let's go ahead and take one more step here to simplify the numerator at least. The denominator I'm not going to touch because, well, that's in a pretty good state to set that equal to 0. So we have r squared plus 1 minus 2r squared. What do we end up with?
R squared plus
Negative r squared plus 1, right? Over r squared plus 1 squared. All right, so to find critical points here, what are we going to set equal to 0? Yeah, really just the numerator, right? So if we want to set the derivative equal to 0, then that's going to be when the numerator equals 0. So we do need to set the numerator equal to 0. So we'll say negative r squared plus 1 equals 0. And we'll get some critical points out of that. We'll come back to it. When else might we get critical points, though? It's not just when the derivative equals 0, but when the derivative is undefined. What in this problem here would make the derivative undefined? If the denominator is equal to 0. So we're also going to set r squared plus 1 squared equal to 0. All right, so we're going to get critical points here because that's when the derivative equals 0. We're going to get critical points here because that's when the derivative is undefined. Now, is this ever going to equal 0?
Nope.
No, because r squared is always going to be positive. If we take any positive number, or 0, 0 is the smallest it could be, plus 1, we're going to get 1 squared, and it's always going to be bigger than 0. So we don't get any critical points out of that one. Nothing's going to happen there. But you still want to check to make sure. You want to set the denominator equal to 0 and check to make sure. How about the other one? What can we do there?
Subtract 1.
Okay, we could subtract 1 from both sides. I would probably factor it, but that's just the way I would think about it. This is the same thing as 1 minus r squared, right? And that would be 1 plus r, 1 minus r. But let's go ahead and subtract 1 from both sides. So we get negative r squared equals negative 1. That's the same thing as r squared equals positive 1, right? And so that means that r equals 1. Or negative 1. Okay, good. So r is going to be positive or negative 1. So we've got critical points at both of those. You guys agree with that?
Yes.
Okay, so we've got our critical points. Now we need to figure out what those are. If they're going to be minimums, maximums, or neither. So again, we'll make our chart. Our sign chart is what this is called. So we're looking at the derivative, and we're going to separate it with the critical points. We have a critical point at negative 1 and a critical point at positive 1. To the left of negative 1. Now remember, we're looking at the derivative here. So to the left of negative 1, if we put in a big negative number, what are we going to get on top? Say we take negative 100 and we square it. We're going to get a really big positive number, but then there's a negative out front, so it's really a really big negative number. So we get a negative on top. Everybody follow that? If you didn't, you could just try plugging in negative 2 and actually do the work. On the bottom, we're always going to get what? A positive, right? So whatever the top is going to tell us the sign. So on top, we're going to end up with a negative. You guys agree with that? If we put 0 in there, 0 is between negative 1 and 1. We could plug in 1/2 or negative 3/4 or some other random number between negative 1 and 1, but I like 0. If we put 0 in there, we get 0 plus 1. It's going to give us a positive, which also means that every between negative 1 and 1, the derivative is always going to be positive. And then to the right of 1, plug in a big number. What do we get? Another negative. Now, I will tell you it's not always going to change signs. You probably talked a little bit last year in your pre-calc class about when it changes and when it bounces. It's going to bounce when it's a double root, and since we didn't have any double roots here, then that's why it's changing signs every time it equals 0. What's going to happen here at this critical point, at negative 1? It goes from, what's the function doing here? Decreasing to increasing. So it goes from decreasing to increasing. What are we going to get there? Local minimum. At what? -1. -1/2. Okay. And then at this other critical point, it goes from increasing here to decreasing. So we're going to get a local goes from increasing to decreasing. It's going up and then it goes down. So we've got to a maximum. That is a local max at 1/2. That make sense? Okay. Another example then. I forgot to put this one in here, but I want to look at this example because it's kind of important. We haven't seen one like it. Let's say we have y equals 1/x. I want to find all local extrema on this. Now, if you know what this function looks like, which I hope you do, then you know what the answer is going to be here. At least you could probably guess what the answer is going to be here. But let's look at y. Actually, let me change this. Because I want to get a misleading answer here. You know how I like to do stuff like that. What's the first thing we're going to do? Take the derivative. And to do that, I'm going to rewrite the function to start here. So I'm going to rewrite it as x to the -2, which means that dy dx is equal to Okay, good. So -2 times x to the -3rd, which is -2 over x to the 3rd. We good with that? Okay, is this derivative ever going to equal 0? No, it's not. Is the derivative ever going to be undefined?
Yes.
Yes. So it's going to be undefined when x to the 3rd equals 0. So it's going to be undefined when
X equals 0.
x equals 0. So we get a critical point at x equals 0. Okay, we good with that? So let's go back to our sign chart then. So I'm looking at the derivative to the left and to the right of 0. If I plug in a number to the left of 0 into our derivative, plug in a negative number, we get a negative divided by a negative, and we get a positive. If I put in a number to the right of 0, we get a negative divided by a positive, and we get a negative. All right, so our function at 0 goes from increasing to decreasing. All right? So what does that mean? You would think, wouldn't you? It's not.
When you
on the
plug the
domain.
critical point into the original, it's also undefined.
What's that?
When you plug the critical point back into the original function, it's also undefined.
Yes. So this is a critical point, and this is going to happen a lot when we get critical points because the derivative is undefined. A lot of times when the derivative is undefined, the function will be also. Okay, not every time, not all the time. That happens also with absolute value functions where we have an undefined derivative but the function is defined. But in this case, the derivative is undefined because the function is undefined. So even though it goes from increasing to decreasing here, here's what the function looks like. And we would have figured this out when we tried to put it back in to figure out what the point was. But 1 over x squared looks like this. So are we going to get a local maximum here? No, it's an asymptote. So the function is not even defined there, so we don't end up with a maximum. So you have to be careful. The sign chart is very useful, but it can be misleading when we get a point that's not defined on the function. Okay, it can also be misleading when we have a function that's not continuous. which then the derivative would not be defined. So when we get critical points because the derivative is undefined, you have to be really careful about using this sign chart here. Okay, it will work with like absolute value functions. With an absolute value function, you would have a derivative that's undefined, but you would end up with a local minimum or maximum. But you might have to do a little bit more investigation to figure out what's going on there. Does that make sense? Okay, one more example I want to do. And more, I want to look at a picture of a graph and talk about what's going on in the graph. So let's say we have a function with a hole in it that looks like this. And it really doesn't matter what it looks like. This is a kind of specific one here. It doesn't necessarily have to look like that. And I'm going to give this an x value just so we can talk about it. What's happening when x equals c here? Do we have a local minimum, a local maximum, neither? What do you think? I've heard all three answers. I like it. So let's have a little talk about it. I can see why you would think it's a local min. If we were to actually do the first derivative test on this, we would see the functions decreasing to the left and increasing to the right. So that means that at that point, then it should be a local minimum. However, the function's not defined. The function's not continuous at that point. It is defined, but it's not continuous, which also means that it's not differentiable at that point. This right here is a critical point, not because the derivative would be equal to 0, but because the derivative is undefined. Okay, so it's actually not going to be a local minimum. Remember, a local minimum means that the value of the function at that point is less than the value of the function around it in the neighborhood. Okay, so that's not the case. How about a local maximum?
Yeah.
Does it fit the description of a local maximum? Vimal thinks yes. Do you guys agree with him? I also think yes. So the value of the function here is greater than the value of the function in the neighborhood of that point. So if we just look around C, I'll put the parentheses down here. If we look at the points around C, the value of the function is less to the left and to the right than it is at C itself. So this is a local maximum. When we have a hole that's defined at a different point than what would make the function continuous, then you're going to end up with a local minimum or a local maximum there. And it doesn't have to look like this. Like I said when I was drawing it, I was drawing kind of a specific example. But we could have something that looks like this also, where it's a straight line otherwise, and then it's defined like that. And the same thing is true here. At C, this function has a local maximum. Okay, it fits the definition of the local extrema that we talked about yesterday. So even though the derivative here, if it were a continuous function, the derivative would just be a constant, and it would not be equal to 0. The derivative is undefined, so we need to look at it more closely and see what's going on. In this case, the value of the function is greater than the points around it. That make sense?